Okay, hello everyone. Another Friday, another session of Amplifying F# as usual. Yeah, welcome. We have a few things to talk about as always before we really dive into the session of today. Let me share my screen so you know what I'm talking about. All right. So as you can see, with this nice little merge label here, Edgar's work has finally been merged last week. If you are interested in the making of this PR, you can rewatch our session. It was like 2 weeks ago, I think. And because Edgar, yeah, can't be stopped, he also got another one nearly merged. He's working on this one here. Another improvement for error reporting because it's like the main topic of Edgar's work, and yeah, he's really improving the developer experience for all of us, because yeah, better error reporting really helps not only newcomers but also more experienced F-sharpers to be more productive and get the job done faster. So another thing from last week, Jimmy talked about his issues, his questions as a maintainer. And as you all know, he's one of the main developers of FS Autocomplete, the LSP that powers Ionide. And that was moved from the FS Projects organization on GitHub to the Ionide organization a couple of days ago. And yeah, we really hope that this helps with the maintainer situation there, especially for Jimmy, as he is doing a great job and really deserves all the help he can get. And speaking of maintainers and yeah, the troubles they have, you all have heard about the XZ drama. Yeah, personally, I scrolled through Mastodon a couple of hours after this last week's session, and then the news hit, and yeah, over the weekend, yeah, it was really a big story, and it deserves all the attention it got because yeah, if this one guy hadn't found the backdoor, yeah, we would be in deep trouble as the internet community. So that again shows the importance of healthy maintainership, healthy open source structures. So we want to remind you guys of our burnout hotline, if you want to call it that way, because yeah, don't think F# can't be a target of such an attack. F# is used for financial modeling, and yeah, it might actually be an interesting target for attackers to place something in some F# package. And of course, if you want to help us financially, we still can only ask for donations in our open collective. There are still people showing up with some donations, and we are really thankful for this. But yeah, it's not on a level that will really make things sustainable on the long run. So yeah, if you can, please talk to your superiors, because we need some companies to chime in this initiative. And last but not least, the essential sessions are still ongoing every Wednesday with Ian and Edgar. As far as I know, it's going still quite well. The crowd enjoys it, and yeah, there's still a couple of weeks left. If you missed some, there were always the recordings. So yeah, give it a try. So if I haven't forgot anything, we can go to today's topic, which is FsLexYacc. This is the port of Lex and Yacc to F#. It's a so-called parser generator, and today we will use it to make this whole pipeline you see right here usable in a little language we will design ourselves today to show you what is actually happening when you compile some source code. The so-called lexer eats your source code and it produces tokens, and these tokens are eaten by the parser, and the parser produces an AST, an abstract syntax tree, and this is processed further by the compiler or some interpreter. And as the result of the compiler or the interpreter, you get a compiled program, or in case of an interpreter, you get your interpreted program and the result of it. So today we will do all of this, of course, in little tiny baby examples. But yeah, at the end of this 60-minute session, I don't know, we will have our own little language with all these parts working. Okay, so as a small reminder, what are these things we are talking about today? What is used for making all this happen? Automata accept words from a language, so they are kind of validators, if you want to call them. They say, yes, this word is part of the language, so this source code is valid, or no, this source code is not valid, for example. Grammars are used to produce words from a language. A word in this meaning, in this context, means a valid source code. For example, some valid F# file is a word from the language F#. Okay, speaking in CS terms. And parsers, they produce trees, and these trees give information about the syntactical structure of the processed source code. So parser generators make use of all these things. They are, of course, equivalent, but yeah, that should be pretty much enough of our little reminder about computer science. So parser generators, they generate parsers from grammars. And as we said, grammars, they produce trees. And FsLexYacc is a parser generator. It's written in F#. Of course, you will recognize these terms, Lex and Yacc. They are pretty old workhorses in the programming world. There's also, for example, Bison, which is another parser generator or compiler generator. Sometimes these terms are used interchangeably, compiler generator or parser generator. And in case of FsLexYacc, it produces an LA-LR parser. LA-LR is the look ahead left-right parser in the taxonomy of parsers. It's a bottom-up parser, and this means that the input that the parser tries to reduce the input to the start symbol and not the other way around. It doesn't start with the start symbol of the grammar. It starts with the real input. So that's the meaning of this bottom up in this little categorization of the LR, LA, LR. Okay, so if you hear the word parser, it's often used as the combination of Alexa and the parser, but today we want to be strict. Alexa is something different than a parser. The Alexa is the lexical analyzing or the scanner or the tokenizer of a piece of source code, and it produces the input for the parser because the parser processes tokens produced by the Alexa. So another word which might come up in the parsing world, especially when we talk about FsLexYacc, is reducing. It means to replace a sequence of symbols matching the right-hand side of a production rule with the non-terminal symbol, which is the left-hand side of the rule. We will see examples of this later on, but this is how the parser makes actually the decision if your source code is valid. If it can't reduce all your source code to the start symbol, to the little one word start symbol, it's not valid because it hasn't found a way to reduce all of your syntactic structures back to the start symbol of your grammar. So that's how the bottom up works. And shifting, this is a word actually for pushing something on the stack. Of course, the parser uses a stack to have the next token to process ready. And if the current state of the parser allows for the next token to be processed, it is put on the stack or shifted onto the stack. Okay. So the next somewhat theoretical thing we need to talk about, what are the boundaries between Alexa and the parser? What should be a token? What shouldn't be a token? And all that. So there are some very broad guidelines here. Alexa should discard everything that is not needed later. So in your AST, you might not need a lot of super detailed white space information, for example, if you choose to not make use of it in some developer tooling later on. And things that the parser needs to distinguish, of course, they should be modeled as different tokens. Because if the parser needs to differentiate, example for between two keywords in some declaration, you make the job of the parser way harder if you give it just one token which represents both keywords. It's better to use a dedicated token for both keywords. That's just one example. And yeah, last things that the parser does not need to distinguish could be grouped into one token. When you develop a language which is a little bit more complex, it's not uncommon to change your design of tokens in the first couple of implementation sessions of the parser and Alexa. All right, so let's dive in. We will create a little example language, like I told you. I have some script here. Let's call it AFLang. It's just a simple project of an implementation project and a test project. Oops. Okay. So as you can see, we have our implementation project and our test project. And yeah, we first need to add the package. So let's do it. All right. And by adding this package, there were special MS build targets added to our project. They are, for example, called call FsYacc. The other one is called FsLex. And yeah, if you compile your project, these targets will be automatically called by MS build, and yeah, the magic happens behind the scenes. So yeah, it's pretty easy to use. There's just a little bit of editing work we need to do here in the FS project file. If you go to the documentation page, you will come to some example. We can just copy that one. And what does it mean? Well, it means that our parser is called, or the file of our grammar, which is always an FSY file, is called parser. And with these special flags here, the MS build target knows that it should process this file. So we can now call it and see what happens. It will likely fail because it can't find the file yet. So let's add a file called parser FSY. Look out for the white file ending. And yeah, now it's found, but of course the content is not correct. Are we FSY? Okay, so let's add some content to it. What's the basic structure of a YAC file? So you have the so-called top code up here between these percent curly braces, and this is regular F# code. You can open, or you should open namespaces and modules. You can define helper functions and all that. It's really just F# code between these two special symbols. Then you define your start token. This is the name of the token which the parser tries to reduce to in the end. And if it can reduce all your source code to the start token, it's a valid word in the language or a valid source code. And then you define all your tokens which are used by the Lexer. And now you already see why we are starting with the YAC file. So if you remember, the parser processes the tokens which are produced by the Lexer, but you define these tokens in the parser. So it's a good idea to start with the parser and then go to the Lexer, or as we can see, even to the AST first before going to the Lexa. Okay. Going back to the basic structure, after the tokens, there were some precedents and associativity rules. We will come to this one, and here you can define the types of your production rules. So this is, if you annotate the type with start, that is really the final type that should be produced by the parser. So if you want to produce some expression, like in this example here, expression option will be the final result of the parse function. Interesting enough, you can also define multiple type lines with other types here. So you are free to produce other types in the other production rules. I will give you an example later on. And yeah, now we are coming to the production rules. The left-hand side is the rule name. You have matching expressions with terminals and non-terminals. Terminal means this can't be reduced anymore to some other rule. It's for example already a character which can't be reduced to something else. Non-terminal, of course, means it's a rule like, for example, that expression or something like this, which could be further reduced and reduced, to some more abstract representation. And what you see here in these curly braces is again just normal F# code. Don't be surprised that you see dollar signs here, $1. This means produce the matching thing, so or the matching parameter. It will make sense when we dive into the implementation later on. So as you can see here, for example, in the expression which matches an int token from the Lexa, we produce something with the name int and the matching token value. So what is this int? This int in this file example needs to be an expression. So we are in the situation that we are kind of going backwards from what you might think is the process of defining all this pipeline. We don't really start at the start of the process pipeline. We start more at the end, because it makes sense that we define these AST substructures so the parsing file actually can use it. So yes, we will copy this one here to our parse FSY, but we will quickly go to the language definition actually. But yeah, let's see if we can already use this. Of course, that's something we still need, our AST namespace. Let's call it, what was the name? AFLang AST. And in this module, we will define this type here. So the parser has actually something to work with or something to produce. Okay, so we add a new file. Let's call it langfs. And of course, we need to edit. And because the parser makes use of this file, it needs to be before the parser file. Langfs.
We also don't need the double dots on line 10, right?
Oh yeah, thanks. Yeah, very good. Okay, so let's define our language. And it's a boring example, but it's a good example because it shows the most important stuff in this in this context here. We will do little math language. Yeah. So we have our expression, which is the root of our AST, and it can be an int of int. It can be a parent, and this has an expression inside. And it can be an infix operator or infix application of a left-hand side expression, some operator. And some expression on the right side. So we need our operator type. And this is, yeah, all the known basic arithmetic. Okay. With this, our parser should be able to build now. All right. So what happened? You can see these new files that were generated for us. And yeah, these files are the generated parser. As I said, FsLexYacc is a parser generator. So there's some auto-generated stuff here, and the things you put in the top code, this open statement is also here. You can see there's some help with the line numbers. If we would, for example, define some helper function and compile again, you can see the helper function appears here in the top code. Our defined tokens like int, left parent, right parent, they also appear here in the auto-generated parser file. But after that, it's pretty much all yeah, internal stuff you don't really need to worry about as a first contact user with this stuff. But basically what happens, yeah, there were yeah, auto generated functions to move between the states of your parser to finally be able to reduce your source code back to this starting symbol. And yeah, okay. So let's see. We have our parser now compiling. Let's look at the rules. So you see here that we are not always producing an expression because if, for example, an empty file would be given or an empty string, we would match on EOF, which is the go-to token of end of file, and in this case we produce none. Otherwise, if there is some source to process or some tokens to process, we try the rules, and there's currently only one rule which matches on an int. And if we match the int token we defined up here, we produce an int expression with the matching thing. So this $1 is just the first thing that matches here. It makes sense what this $1 really means if we do the other stuff. So it could be that we have an expression plus an expression. So for example, 3 plus 5. What we want to do then is we would use something from our language. I put it on the right side so we know. It doesn't make sense to produce an int or a parent in this case, but we produce an infix app. You don't get very good editor tooling here because it's an unusual file format, this FSY, of course. We give it the first matching thing. $1 match is this first expression thing here, whatever it reduces to, and the operator is the add op. I actually need to make a tuple out of that. And the right-hand side of this thing is $3. So this is what this $1 to 3 stuff means. It's the matching things from the rule from the left-hand side. All right. So let's add the other expressions. We have minus, and we will have slash. I need to define it, and let's do the star first and the slash. And this is the add op minus a sub op multiply op and division op. Okay, so I need to define these tokens. It's star slash plus and minus. Yep.
Are you deliberately using star and slash before plus and minus here?
No, not here. But we can play with these things later on and see the effects of orders.
Gotcha.
We will leave these out here first, and yeah, to show the effect of precedence and associativity later on in the tests. All right. Let's see if this still builds. All right. It still builds. So we have now our parser hopefully workable. We have our AST. We can now actually already think about what the evaluation of these expressions should do, because if we do it now, yeah, after the lecture, we are already pretty much in the state to test our creation here. So let's jump ahead and do the interpreter. I will just call it one. It takes an expression. And of course, with the pattern matching of F#, it's pretty easy to write an interpreter for such a thing. It can be an int. So our result is just int. To open some stuff here. It can be a parenthesized expression, and if this is the case, we of course need to evaluate the thing inside. So this of course needs to be recursive. And the last thing it can match on is the infix application. And yeah, we have the left-hand side, the operator, and the right-hand side. So now we need to decide what the operator is, and given on this information, we can call the operator with the left and the right-hand side. So let's say we catch that meaning here in this f function. We say match up with mul up. In this case, we want to multiply stuff with v more. We have the diff. We have add and minus. And the somewhat odd coloring shows you a piece of work for the weekend. Support pattern. All right. Okay, so we can actually apply f on the evaluation of the left-hand side and the evaluation result of the right-hand side. And yeah, that's pretty much all we need to interpret the math language. In fact, we could now write a test for it, but yeah, let's be bold and trust ourselves and go to the lecture. So it's pretty much the same story with the integration of the lecture into our build process. It's not FsLexYacc, but it's FsLex called here. We call it Lexer FSL. We don't need this stuff here, but I think we need Unicode or should have Unicode. Let's take a peek. Minus Unicode to support Unicode. Yeah. And this will look for a file called LexFSL. If it's found, it will auto produce Lexa implementations for us. Let's see if this is in this supposed state. So here could not file LexFSL. That's correct. Let's add such a file. And yeah, this structure of the FSL file is yeah, pretty similar to what we had in the YAC file. I think I talked about this already. I will explain the structure in the source code itself. Okay, so at the top you have again just regular F# code, just like in the YAC file. You have the module name, you open some stuff, and this is the important thing. You need to open your parser module here, because the Lexa, as I said, it produces the tokens which are defined by the parser. So our parser is just the module parser. If we take a peek here in the produced file, it should say module parser, right? Okay, so let's open that one in the Lexa, so it knows about the tokens it can produce. Of course, you can model this in a different way. You could use just the Lexa without FsLexYacc. But yeah, let's keep it simple for today and use them in the way they are pretty much always used. Okay, some helper functions which are always handy to have are also in the top code. We keep those, and after that we see something, a collection of regex macros. Yeah, these are just regex expressions in a regex language defined by the Lexa, by FsLex. And of course, you can come up with your own macros here and use these in the rules, which are at the end of the file here. Funny enough, this structure here, for example, that the top code needs to come before the regex macros and the regex macros come before the rules. These are also defined in a YAC file in the source code of FsLexYacc. Just as a small that's not the one. That's one. As a small detour, this is the code base of FsLexYacc itself, and here's a file called FsYacc parse FSY. And you can see here, for example, in the spec, that there's this header opt, the decals, the percent, and the rules. And the same we have for FsLux parse, FSY. You can see here you have the code at the top, the F# code, the regular expression macros, and the rules. And yeah, you can also have like a footer, optional footer code. But yeah, I thought that was somewhat funny. Okay, back to our Lexa. So we have some basic stuff already defined here. I think we could try to build it now. And again, there's an F# file called Lexa FS produced. And yeah, the same story. The top code is copied here. You have these transition tables or go-to tables, and yeah, the rules we define in our somewhat different Lexa Lex syntax. Okay, so right now we already produce the int tokens. Let's put the parser to the right side so we know what is still missing. We produce the int and we produce the star, but yeah, no minus, plus, and all that. So let's match on these as well. We have the slash. And plus. Minus. And I think that's pretty much all we need. EOF is already matched if the source code is empty, and white space is handled already for us. So yeah, we can compile the Lexa again and include the output of the Lexa and the parser in our program. So as I said, the stuff from the parser is used in the Lexa, so order matters here. Infix app is not defined. I think I have some namespace stuff. Okay, it should be openlang and not the other thing. Okay. So we have our Lexa, our parser ready, and now we can actually start to parse source code. So let's go to our tests. Let's keep it in one editor. And yeah, let's do some basic mass tests. I will add some simple helper function here. So because we are writing a couple of tests, it will be easier to formulate these. And I will steal this one from some example. And we don't pass JSON, we pass source. Okay. As I said, we get an option back, an optional AST back, and so I will catch the stuff up here in case it's not an AST. It just makes for simpler testing. Let's go to the test. I am okay. All right. So now we can have some source code. Let's say 10 plus 2, and we get an AST by parsing this one. And actually we want to run it, so let's open our interpreter. And we assert that yeah, this is like 12. All right, and this is pretty much it. So we have, like, after 40 minutes, our lexer and parser and little own mass creation language implemented in a state that we can now just expand and expand our language with more features and stuff. But there's one thing that we really need to show here, because yeah, this is pretty much the first thing everyone will stumble upon when dealing with language design, language creation. This is associativity and precedence. So let's do a little bit of real testing here first. We will do the left-hand side, the operator, the right-hand side, and the expected result. Catch that one here, left op, right expected. And our source will be constructed by the left-hand side, the operator, the right-hand side, and we want it to be the expected result. And we have 4 operations we need to test. So 10 minus 2 is 8. 10 times 2 is 20, and 10 divided by 2 should be 5. And let's check if this is the case. Okay. So far, our stuff works, but of course, it's pretty obvious for everyone which comes next. And this is the precedence tests. So, for example, if you have something like 10 10 2 times 10 plus 3. It should be parsed as this one, even though the user might not have put in the parentheses. So we get 2 times 10 is 20 plus 3, 23. And it shouldn't be 2 times 13, which is 26. Okay. So pretty basic stuff. Let's do a test for this. So we have the high precedence operator first. So let's say we do it 2 times 10, and then at the lower precedence operator and the right hand side of that one, and the result we expect, which is 23. So we have the left, the high preg op, right, the low precedence op, and the second white one, and that expected result. Okay, this is the high preg op, the right hand side, the second operator, which is lower precedent, and the white 2. And yeah, this should fail now. Because we mess up our precedence with our YAC so far. So what we need to do is what I skipped in the beginning. We need to take care of this one here. So we can say that a rule should be left or right associative with the percent left or percent right. In this case, we want it to be left, and we have like 2 hierarchy levels of precedence we need to define here. That's why we have 2 lines here and not like 1 line. So we say plus and minus, they are on the same precedence level, and also on the same level as star and slash. So this is important in which order you define these. Let's test this first if it works now. Okay, so if we change this order here, if you might think the first one is more important and it somehow has higher precedence, but this is not the case. So yeah, that's something I still want to make a little bit more prominent in the documentation. Maybe if you have dealt with YAC in the past, it's child's play. But yeah, for me it was a little bit surprising when I started with this stuff a couple of days ago. And yeah, so we should have now the precedence correct for our tests, and we can add the other cases. For example, it should also work with minus. So 2 times 10 minus 3 should be 17. And let's also do the other high precedence operator. Let's say we take 50 divided by 10 is 5, plus 3 is 8, and the same thing, 5 minus 3 is 2. Okay, so this is now working for an expression which has the high precedence operator on the left side of the whole expression. Does it also work if the high precedence operator comes on the right side? So we basically switch this stuff. So now we have 10 times 30 is 10 times 3 is 30, plus 2 is 33. 30,
32.
excuse me?
32.
Oh yeah, thanks. And 2 minus 30 is minus 28. And 50 plus 9 plus 3 is 53. Yeah. And again, this 10 divided by 3 is 3. 50 minus 3 is 47. Okay. The right precedence is also working. We could now also test our parentheses, but yeah, let's just go to something more interesting and test it in a REPL, for example, because it's fairly simple to now implement a REPL for our language. So let's say we are in our program module and we have our main function, and this just calls our REPL we will implement. Again, I will take the little helper function for the parsing. Okay, so our REPL does greet the user first with some prompt, and yeah, then we have some mutable input because we need to loop. And we say while the input is yeah, not Q, for example, we let the parser do its thing and pass the input from the user. And then we call our interpreter. We print the output. And yep, prompt again and wait for another input. I think that's enough for a REPL, I hope. Let's go to the okay, there's our REPL. Let's say 2 times 10 plus 3. Okay, looks good. And now for our parentheses test, this should be 26. Unhandled exception, unexpected char. So we should have written a test because our Lexer is apparently not yet handling the parents. So let's fix this. Left parent and right parent. We missed this. Okay. Let's start with the left one. Okay, now the Lexer should produce the tokens, and our parser still needs to know about these as well. So we have a left parent, we have some expression in between, a right parent, and what we want to produce out of this is a parent with whatever matches in between. If we go back to our lang, yeah, that should be correct. Let's build again. And what was it? 10 times 2 plus 3. Okay, looks correct. Yeah. I would leave it at that. It's now all a game of extending your parser, your tokens, the supported expressions in your language up here. F Sharp itself, if you know the compiler code base, you can see the resemblance. I mean, it's just scale which differs here. It might be a little bit of a bold statement, but yeah, to me, this makes kind of sense that a compiler can be that small, and a big compiler just has the same kind of basic structures, the same pipelines, and it just operates on a different scale. So yeah, any questions?
Yes, I have a lot of questions.
Okay.
So I love the FsLexYacc project, but when I try myself, I realized that it sometimes throws some errors on the console saying that there was a shifting reduction warning or something like that. And I was kind of investigating if that is bad or if I should go and fix that. And then I was running the F-sharp compiler, and I saw a lot of those in the compiler itself saying, there is a shifting rule that is not matching some criteria or something like that. And I saw hundreds of them. So are those warnings, or I think there are warnings, I guess, but are those warnings something that shows that your parser or your PS, I think it's FSY or PSY file is not done right properly, or is there a concern for
that? Good question. I don't know. Yep.
I do think it means that your grammar is not unique, that there are multiple paths for what you are parsing possible. That's what I think is behind it. And that the parser resolves it, but by just taking the first option or something like that. That's what vaguely I think it is.
But I think these would be reported as shifting conflicts. I mean, I'm not sure, but
But that's what you referred to, Edgar, right?
Yeah, it's something.
okay.
Yeah, it's because when I the first time I ran the build script on the FsLexYacc compiler, I noticed that there were hundreds of them. I was like, what? Maybe I did. I thought I broke something on the compiler, but then I realized that is the output that the library, I guess in this case, FsLexYacc, it is providing, saying that there's a conflict, I guess, on your as you said, your rules, and I guess it's easy to kind of work around or just try to fix them in a language, creating a language from scratch or in a small subset of in a small language like this, that in a toy language rather than a huge language with the multiple rules, because I tried to fix one of those ones and I end up just basically abandoning that because it was complicated.
I mean, there's this precedence direction, or I don't know how to call it, to break these these situations of reduction conflicts. But I don't know if this would help in the F# compiler case. We might need to investigate and try. But
the other question is, of course, do we really need all that output, right? I also stumbled upon it when I first built the compiler, because it always appears and probably nobody looks at it.
Yeah, it's compiler porn I enjoy. So.
Was the other one was like so there must, what was the decision for you? I mean, I know maybe this is something historical we don't know, but what were the advantages of using something like this instead and not creating a manual manual parser that most of the languages nowadays they use Rust, or they use something else to be able to generate their language.
Well, if you have implemented the generation correctly once, you are able to use it for multiple languages. And if you do it from scratch for all languages, I think the chance of having a bug is way higher.
Yeah, because I think I saw in a presentation somewhere that there was this is really F# is one of the few languages that use this kind of mechanism because it has some properties of this that will make it unique, I guess, or something like that. But yeah, I need to investigate more on that as well. It's something that I really don't know exactly what was the reason and why they even what was the reason to create FsLex or FsLexYacc in the first instance.
Okay, yeah.
Thank you.
Okay.
We have I think a couple of questions in the chat. Let's see. Yeah, something about the performance of LFJX, FsLexYacc. There's a link on the chat as well.
As far as I know, there's no one working on the performance. But yeah, I mean I chose it because it's just super nice to work with from an F# point of view. But yeah, I don't know. It might have been superseded by other implementations by other algorithms by now. That's well possible. Yeah.
Does parsing take a significant time in the whole compilation, or is it not all type checking?
I think type checking is still the monster piece compared to parsing. Yeah.
I would assume some newer .NET constructs could make FsLexYacc a little faster. Think of spans and the new memory stuff and whatnot. But yeah, pretty sure nobody's really actively working on that. So progress, folks.
If you grab the source code of FsLexYacc for to-dos, you will find some hints for performance work. But these are pretty old, and yeah. Okay. Should we wrap up for today? I guess we do.
Yes.
All right, cool. Yeah, then thanks for joining us. Try FsLexYacc or your another parser generator. It's fun. It's really fun. Once you get the hang of it, yeah, you really enjoy writing your own little language, adding more and more constructs to it, and yeah, you lose the fear of the big compilers, the big Lexus and YAC files in the process. So it's a worthwhile evening spent.
So I think it's worth to mention that I think we have also a session on. I mean, it's not really. We have a session on the. I think it's
parser recovery.
Yeah, parser recovery as well. Someone's interested as well with the native gene. So yeah, it would be.
Exactly. Yeah. All right. Cool. Yeah. Then it's time to say have a nice weekend. See you next time, next Friday maybe.
Yep.
Bye.
Thank you.
Bye.
Bye.
Thank you, David.